welcome to Wednesday's edition of Cracking the Cryptic, where today we've got a puzzle called Quatre Coins for you, and I think that is French for four corners. And if it is French for four corners, I think I have done the original Four Corners puzzle by Toolcat, and this is the sequel. Now, the testing reports on this are that it is an absolutely mesmerising puzzle, and I have to say I do have a soft spot for these puzzles that look like geometry is going to be interesting. So we've got the two diagonals marked, some arrows, some Kropki dots. There definitely seems to be some structure to this one, so I'm going to give it a go in just a moment and read you the rules. But it is coming up fast on the 1st of August, and that means if you are a patron of the channel over on Patreon, you will be wondering what your monthly reward is for August. And it is in fact a puzzle pack created by none other than Grockles, the astrophysicist. You'll be very familiar with the work of Grockles if you've been following the channel for any amount of time. And Grockles has created a rather special set of puzzles based around thermo Sudokus of differing lengths. So basically there's a whole puzzle dedicated to thermos of length 2. Then there's a puzzle dedicated to thermos of length 3, etc., all the way up to 9. And Grockles has even thrown in a slow thermo at the end to make 9 puzzles in all. So this is very exciting. The puzzles themselves are absolutely brilliant. You'll love them. So we're going to release that on the 1st of August, and I think what we'll do is we'll do what we did last month. It was so popular with Jovial's Sudoku Extravaganza that we will draw a name out of the hat to win some merch. So if you do manage to finish them all, send us the solution and we will put your name in the hat for merch. I think we ended up getting something like 1,000 entries to Jovial's one, which is fairly extraordinary. Anyway, that said, what else do I want to say? Nothing, I don't think. Just to let you know that was coming. It's nearly here. Now I should read you the rules to Quatre Coins. They are as follows. Normal Sudoku rules apply. Good. Digits along an arrow must sum to the digit in that arrow's circle. So that's normal arrows. There's actually only 4 arrows by the looks of it. So that means what we do for this arrow is we add those 3 cells and plonk the result into that cell. Cells separated by a black dot must contain the digits. Must contain digits with a ratio of 1 to 2. So there's only 1 black dot actually. So this could be something like 3 and 6 or 4 and 8. We just have to make sure they're in a 1 to 2 ratio. Cells separated by a white dot must contain digits that are consecutive. So those, well, there's actually loads of these, aren't there? So we just have to make sure white dots are consecutive. Now there's no mention here of a negative constraint, so I'm going to assume there is no negative constraint and hope that's not a mistake. Normally it would say so what do I mean by negative constraint? Well, let's consider this domino here, which doesn't have a white or a black dot. I'm assuming this can contain consecutive digits or can contain digits in the ratio of 1 to 2. So in other words, what the dots are doing is providing positive information. The absence of a dot doesn't tell us anything, and that's the normal way round. So hopefully no one's messed up and I've been given a puzzle that will actually solve. Now, each main diagonal marked in blue cannot contain a repeated digit, so that is fairly straightforward, hopefully. So that means that diagonal there, we've got to make sure basically it contains all of the digits from 1 to 9 once each, and the same for the other diagonal. So, do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And right, well, the first thing I can see here is something I think I've seen in other puzzles which have this sort of geometry, and it relates to those squares. Now, the most obvious thing about these 4 squares is that because each of them has an arrow, a 3-cell arrow emanating from the circle, because the minimum we could put in an arrow would be 1, 2 and 3, each of these digits is going to have to be a 6, 7, 8 or a 9. Because 1 plus 2 plus 3 equals 6, and we can't therefore go lower than 6 into the circles. But here, look at the diagonals. Look at the effect the diagonals have on these cells. This square actually sees all 3 other squares. So whatever's in there, let's imagine this was an 8. you now can't put an 8 in those by Sudoku and can't put an 8 in there because of the diagonal. In other words, all of these digits must be different, and that gives me an opportunity, yes, you've guessed it, to colour them in. That's what I'm going to do, to remind me that they are all different. Now, so one of these is a 6, which will have to be a 1, 2 and a 3. One of them will be a 7, which will have to be a 1, 2 and a 4. The 8 will have 2 options, the 9 will have 3 options. Okay, well the next thing I'm seeing, and I don't know if this is relevant or not, but I'll mention it in case, is that each of the corner boxes has exactly 2 white Kropki dots, and those white Kropki dots are never on the arrows. Look, I'm not sure what that means, but what does that mean? Is that providing some sort of restriction? Yeah, okay. Right, well the most obvious one is the 7. I don't know which of these is a 7, but let's just imagine it's this one. The 7 will have 1, 2, 4 on its arrow for certain. And therefore, if you think about the string of digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, imagine the 1, 2 and the 4 are sort of highlighted. What do we do with the 3 in this box? The 3 can't go on a white Kropki dot, because if it did, it would need a friend in the form of a 2 or a 4, but the 2 and the 4 have been hypothecated to the arrow, so that's not possible. So the 3 would always go here. So that wherever the 7 lives in these boxes, the 3 is either there, or there. Okay, I'm not sure what I can do with that. So, but that, okay, there's something going on here, I think, with the white dots. I'm just not quite sure I know what it is. Maybe we can stop. Yeah, for instance, the 9. Wherever the 9 is, let's imagine this is a 9. Just, oopsie, I want to imagine it is a 9. This is a 9. Now, there are 3 ways of making 9 in 3 cells. One of them is 1, 3, 5. Now, that's not going to work, actually, because if we go 1, 3, 5, and we've got to find 2 consecutive dominoes out of the digits 2, well, the simplest way to see why 1, 3, 5 doesn't work is to think about the example of the 3 with the 7. You can see here that we need to put 2 and 4 in this box, and the 2 and the 4 can't be next, or we can't place them in the white dot squares because the 1, 3 and the 5 are not available to them. So the 2 and the 4 would have to both go in this square, and you can't have a square that simultaneously contains a 2 and a 4 at the same time. There are no such things as Schrödinger cells in Sudoku. So the 9 is not 1, 3, 5. So it's either going to be, now let's check, it's either 1, 2, 6. I see. 1, 2, 6 would work. You'd have a 7 and an 8 on one of the white Kropki dots. And then the other Kropki dot would be a 3, 4 or a 4, 5. Alright, let's try the other one. So if it's not 1, well, it could be 1, 2, 6. If it's not 1, 2, 6, it's got to be 2, 3, 4. And okay, straight away we can ask the question about the 1 there, and the 1 would have to go here, because the 1 can't be consecutive with the 2 now, so can't go on a dot. This is very interesting. So now, so we know 9 is either 2, 3, 4 or 1, 2, 6. Let's think about 8. Let's make this 8. Whoa. Let's make this 8 now. So 8 is either going to be 1, 3, 4 which hypothecates the 2. Oh, no, it doesn't. Oh, that's interesting. The 8. This is beautiful. Right, the 8 is a problem. Well, it's not a problem, it's a solution. Because, yes, the 8, the moment you put 8 in the circle, the 9 is instantly a problem in this box. The 9 definitely has to not go on a Kropki dot because it can't be next to the 8. But here, the 2 has become a problem as well, because the 2 can't be next to the 1 or the 3. So this would have to be a Schrodinger cell that was a 2 and a 9, which won't work. So the 8 has to be 1, 2, 5, I think, which will work because that will allow room for the 3, 4. The 9 will go in the corner, and you'll have 6, 7 in the other Kropki dot. Wow, okay, so now I'm almost tempted to get my notepad out. Let's try and do it. We'll try and do it in our heads and keep track. And if I get stuck, I'm going to get a notepad out. So, the 6, wherever it lives, is 1, 2, 3. The 7 is 1, 2, 4. The 8 is 1, 2, 5. And the 9, we don't know. It's either 2, 3, 4 or 1, 2, 6. But what does that allow us to do? Well, I think every single one of those options had a 2 in it, which means that every single arrow has a 2 in it. And if every single arrow has a 2 in it, what does that mean for the diagonals? We've got to put 2s on both diagonals that aren't in the corner squares. In other words, there has to be a 2 on this diagonal in one of those 3 squares and this diagonal in one of those 3 squares. So the middle square has to be a 2 to simultaneously fulfill those criteria. That means that square's a 1 or a 4 because of that Kropki dot. Right, now, how many of those options had a 1 on them? The 6 had a 1 on it, 1, 2, 3. The 7 had a 1 on it, 1, 2, 4. The 8 had a 1 on it, 1, 2, 5. And we didn't... Oh! Well, I was about to say we don't know about the 9. And we now do know about the 9. Because what would happen if the 9 was 1, 2, 6? Well, if the 9 was 1, 2, 6, every arrow cell would have a 1 on it as well, and we'd have to put a 1 simultaneously in the middle square as well as a 2, which is impossible because the 2 is not, just as this square wasn't a Schrodinger cell, neither is the central square. So we've now learnt the 9. The 9 is 2, 3, 4. But we also know about the 1s. This is just an absolutely beautiful puzzle. And why do we know about the 1s? Well, I know that 3 of the arrows, I don't know which arrows they are, but I know 3 of them have a 1 on them. Now, if 3 of them have a 1 on them, there must be ones either, let's imagine this one doesn't have a 1 on it. If this one doesn't have a 1 on it, these 3 will have 1s on them. And that means you'll have to put a 1 on this diagonal in one of those 2 squares. But that logic obviously works if you just assume there's no 1 on this one. If there's no 1 on this one, you'll have 1s in these 3, and then you'll have to put a 1 on this diagonal. So the key point is that there must always be a 1 in one of those, not one of these 4 squares in the central box, because we're going to have to put a 1 on the diagonal in the central box in one case, in exactly one case. And that means, what can this square not be? That's it, 1, that's a 4. Now I'm very tempted to look at 4s. What do we know about 4s? We know that the 7 arrow has a 4 on it. And we know the 9 arrow has a 4 on it. Right, okay, but let's think about this for a second, because if we can't put 4 in any of those 4 squares, and we can't, yet both diagonals have to have a 4 on them. There must be a 4 in one of, one of those 4 squares there. And there must be a 4 in one of these 4 squares here. Well, So there must be one 4 in yellow and one 4 in orange. That doesn't actually seem to be immediately helpful, does it? How do we work out where that 4 goes? Maybe it's not 4s. So what have we now got on the arrows? And this is a bit tricky because I still don't know which one's which. But we've got a 1, 2 and a 3 on the 6 arrow. Now that one, I'm wondering if I can get the... Can I isolate the options for the cells that are not on the Kropki dots? Is that a silly idea? Because for the 7, we know it's a 3. So one of those squares has to be a 3. For the 8, we know it's the 9. For the 9, we know it's the 1 because we've got 2, 3, 4 on the arrow and the 1 is isolated. For the 6 is most irritating, isn't it? It's most irritating because the 6 is a 1, 2, 3 arrow, which means 4 and 5 are on a Kropki dot. And then 2 of the digits 7, 8 and 9, which means 8 is on a Kropki dot with a 7 or a 9, but we don't know which. So the other thing is, so I have to add 7 to those options. But I don't, for example, if none of those contained a 7, this would be a 1, 3, 9 triple because they all see each other. But I see. Okay, I see. No. Well, no, I do see. I sort of see, and now I think I do see. Good grief, this is clever. Right, okay. So, this was worth doing, not actually because of what goes in the 1, 3, 7, 9 cells, but because of what we need to put on the diagonals. I need to put a 4 in yellow, which apparently can't go in those two anymore. And I need to put a 4 in orange, and that can't go... This is a 4, isn't it? Oh, this is so close. Right. I need to put a 4 in orange, and I need to put a 4 in yellow. Now, if I put a 4 here in orange, where do I put the 4 in yellow? The answer is nowhere. This 4 rules out the only 2 cells that can be a 4. So that's not a 4. But if that's not a 4, where do I put 4 in orange? There. That is a 4, which means that is a 3 or a 5. Now this is not a 4, because we only put one 4. Well, obviously it sees this cell on the diagonal. So there's now a 4 in one of those 2 squares. I have no idea really how to pencil that. I'll do it like that. Now, does that limit this square or not? Well, yes, it does. It means that... yeah, it does. It does, actually. It means that square's not 7 and it's not 9. Because for 7, we know it's a 1, 2, 4 on the arrow. 9, we know it's 2, 3, 4 on the arrow. This now has to be 7... Sorry, it has to be 6 or 8. 6 would put 1, 2, 3 on the arrow. 8 would put 1, 2, 5 on the arrow. Ooh, so this is some sort of quintuple then. If this is 6, we've got 1, 2, 3. If it's 8, we've got 1, 2, 5. And look, those squares are all low digits. So this square is now... Oh no! Nearly. This is a 7 or a 9. I thought we might get it then, but we haven't. So these are 6, 7, 8, 9 in some order. And now what? So now I know that either this digit or this digit is a 6 or an 8. Because I need to put 4 off the arrow in exactly one of these boxes, don't I? If these boxes were a 9-7 pair, then I'd have 4 on the arrow in both instances, and I wouldn't be able to put 4 on this diagonal. So that's right. So one of these is a 6 or an 8, which means this square is not a 6 or an 8, and that's a 7 or a 9. Which means these squares are either 2, 3, 4 or 1, 2, 4. 2, 3, 4 or 1. No, I can't. No, okay. Now I've got a 7, 9. Oh, sorry. Yeah, look, I've got a 7, 9 pair on this diagonal. This square and this square, so that's not 7 or 9. And that's given me a quadruple in box 3, which means these squares are now 5, 6, 7, 8, 9. Oh, this is very, very close to cracking now. These are both white Kropki dots, so if that's 9, you go to, oh, no, it works. You go 2, 3, 4, 1, and you get 5, 6, and 7, 8. And if that's 7, you've got an 8, 9 Kropki dot. This becomes a 3, and you've got a 5, 6 Kropki dot. Ah, right. Goodness me. Okay. So is there going to be a way of determining which one of these is 6, 8? That white Kropki dot looks a bit... If that's a 6, 8, does that white Kropki dot break? Yes, it does. It does. By parity. That's a simple way of seeing that. If this is a 6 or an 8, let's show this. Now look carefully at this white dot. One thing we know about a white Kropki dot, because the digits are consecutive on it, they must include an even and an odd digit. Which even digit are we putting into this white Kropki dot? It can't be 6, it can't be 8, and it can't be 2. So it has to be 4. But the moment it's 4, we've broken the puzzle. Because we then can't put a 4 here. And we won't be able to put a 4 here because this will have a 7, 9 on it, and this will have a 4 on it. So there's simply no way this works. We need this. Well, if this is 6, 8, we run out of even digits. And we mustn't run out of even digits, so we've got to put 7, 9 in there. Now I've got all sorts of things going on, because this has got to be a 6, 8. These squares are then either 1, 2, 3... or 1, 2, 5, we now know that the 4 must go here in order to allow this diagonal to have a 4 on it. Do we know anything else? Yes, we do, because this is on a white Kropki dot, so that's a 3 or a 5. So that gives me a quintuple, removes 1 and 3 from this square. That gives me a 7, 9 on this diagonal, which means this square is not 7 or 9. Now we've got the quintuple there. So this is from, oh, I see, this is 6, 7, 8 or 9. But until we know what this is, we don't know what this is. And we've got a 7, 9 pair here, which means that those squares aren't 7 or 9. Aha! So how does this Kropki dot work? Well, they need to be consecutive, so there's no 8 in them. Which means those squares are not 5, 6 anymore. So there's definitely an 8 in one of those squares. And the diagonal is rather interesting now because that has a 7 and a 9 on it. So that square is an 8. This square is therefore not an 8. That doesn't seem to tell me all of the secrets I might need it to tell me. Okay. So what do we do with this newfound information? Probably we have got to... I haven't got a clue. You know I'm buying for time, don't you? Come on. Maybe I've got to pencil mark this one. So this is either 1, 2, 4 or 2, 3, 4. So again, I've got another 1, 2, 3, 4 quadruple here. Oh, and in fact I've got a 1, 3 pair here. So this square is a 2 or a 4. This square is a 2 or a 4. And these squares have got to be from 5, 6, 7, 8 and 9 again. Let's make sure we include all of the digits there. Which means that... Oh, this 8 I've just seen is seeing that square. Oh, this is good. This is good. The 8 is giving us knowledge. It's giving us knowledge. This is a 6, which means this is an 8. Which means those aren't 8. Now we can't put 9 on this crop key dot. Oh, this is massive, absolutely massive. 9, that becomes a 7, that becomes a 9. So this 8's actually done an awful lot of work because now, now I know all of these and therefore I know all of their arrows. This one has not got a 3 on it. So that means this square is a 3. That means that square is a 1. That means these squares are 2, 3 and 4. Don't know if we can figure that out. This is a 1, 2, 3 arrow, which means that square's a 5. And this arrow has not got a 3 on it because we know this arrow is 1, 2, 5, and there's a 1 here. Oh, in fact, there's a 5 here. So that's a 5, that's a 1, that's a 2. Now that's no longer a 2. This square's become a this square's become a 3, which gives me the 3 over here. I don't believe it. There is a chance this puzzle will actually... It might crack here. It might give me... It might give up its secrets. Oh, not quite. Oh, the 9 here is giving me a secret. That's a 7. So 7, 8, 9 here. We remove 7, 8, 9 from that square. This is a 5 or a 6. Does that tell me? Yes, it does actually, because 7 can't go in any of these. So this has to be a 5 or a 6 as well, which means this is an 8 or a 9, and there's an 8 here. So this is all getting resolved. That's a 4, because it can't be a 3. That means that's a 2 and that's a 3. That means that's a 4. This is an 8. And this is a 9, just using the 8 here. This 7 is giving me a 7 and a 6. This 5 is giving me a 5 and a 6, and that means that's a 7. That's giving me a 5 and a 6 over here. Yes, I will agree. The way I scan puzzles is strange. Now, what does all this mean? I feel like we've broken the back of this. We've got 2 unused crop key dots to use, but we have an awful lot of real estate filled in. What are those squares? 1, 2 and 7. Well, that's not a 2. And that's not a 1 because it's on a crop key dot. So that would have to be a 2, which it can't be. So that's 7. These squares are 5, 6 and... Oh, we don't know anything about those. 5, 6 and 9. Therefore, these squares are 3, 4 and 8. That's not a 4. And we don't know anything about those either. Yeah, so it's probably this crop key dot that's going to do work. But let's do some pencil marking. 3s, 4s and 7s there. This is a 3 because it sees 4 and 7. That means that square's an 8. These squares have got to be 1, 2 and 6. That's not 2. 7 means that's got to be consecutive with 7, so that's 6. This is 1. We need a 9 in this column, which we can put in either of those positions, and we also need a, no, not a 3, a 5, is it? Can we get rid of a 5 from either of those? Maybe not. Okay, let's complete the pencil marking down at the bottom, where we need 5s, 8s and 9s. Not that. Goodness me. Right, that. 5, 8 and 9. Oh, I know what I should look at. Look, these diagonals. I've done them, basically. I know what those two squares have got to be. They have got to be 1 and 6. These two have got to be not 1, therefore, because there's only one in the central box. Those squares are 3 and 5, maybe? Oh, and that means that's a 9, so that's a 5. And those squares have got to include 8. I can see, that, is it 7 and 8 actually? That's a 7-8 pair. So what is it that this crop key dot's meant to be doing? Maybe we'll look at that digit. That digit's got to be 1, 2, 3 or 6. Doesn't seem to be immediately. If that is, I don't know. If this is 1, that means this square would be a 2. If this is 2, this has got to be 1 then, because it can't be 3. Oh, this can't be 1 or 2. Oh, I see. Oh, it's because there's a 1, 2 pair in this column. That's what I hadn't appreciated. So in fact, this digit is far more restricted than I realised. That square, oh, this square's a 7, 8 or a 9. Just look at that column. That's what we had to spot. 1, 2, 3, 4, 5 and 6 used. This is a 7, 8 or 9. Given this is 1, 2, 3 or 6, the only way this works is 6 and 7, which gives us a 1 here and a 6 here and a 6 here and a 2 here and a 2 here and a 1 here. Those two squares aren't 6 anymore. Wow, is that really all we're going to get? Because that still seems to be, there seem to be a lot of things that need resolving in the middle. It's going to have to be this 3, 5 that disambiguates the entire, well, the entirety of column 4 and column 6. Nah, okay. Let's have a look at the rest of this column. We need to put in 8 and 9, which we can do. So that's 9, that's 8. We can place 8, therefore, in box 6, just by Sudoku using the 8s. These two squares have got to be 6 and 7, which does resolve. Okay, good. 6 and 7 go in. This column needs ones. That's a 5. Look. Yeah, we need 1, 4, 5 into those, but there's a 1, 4 there. That becomes a 5. That's going to finish the 3, finish the 5. That gets the 5 and the 9 disambiguated, the 9 and the 8, the 8 and the 7 and the 4, the 4 and the 3. So that's how all of that was meant to work. Now we get a 1 and 4 here, we get a 2, 3, 9 over there. 9 must go at the top. 2 must go here, 3 must go there. Now this square's got to be a something. He says, trying to get his scanning up to speed. This is a 2, so that's a 2, that's a 1, that's a 2, that's a 1. This box now needs what? 1s, 3s, 4s and 5s. So this is a 4, 5 pair, so that's a 5, that's a 4, 4, 4. 1, 3, tick. Yay! That is an extremely beautiful puzzle. It really is lovely, lovely logic. This stuff, the fact that you can start this puzzle and actually work out ab initio what is on each of the arrows, and then you can work out, because of the white crop key dots, that there's a restriction. Well, there's a restriction on 2s and 1s. We got that. And this black crop key dot forcing the 4, and then the way the 4 is potently powerful because of the white crop key dots it's superbly clever. It really is. And it's just the way that Toolcat has arranged the white dots so that you can actually disambiguate the order. I don't really quite understand how that was done, but it did seem to be the case, didn't it? Because we ended up with having to put a 4 here, because a 4 here would have eliminated the possibility of a 4 on the other diagonal. Mind-blowing, absolutely mind-blowing. I hope you enjoyed it. Let me know in the comments. I do enjoy reading them, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.